let me tell you a little bit more about this equivalent circuit for the resonator. So I'm going to draw L, C, and R, LX, CX, and RX like this, right? And so just so that I have like a ground terminal on each side. Remember, what we're going to do is basically this is the motion current, and then this is our drive voltage, Vn plus and minus like this, okay? And before, what I did was I wrote that Lx is equal to the mass of the resonator divided by eta squared, and Cx is equal to eta squared over the spring constant, and Rx is equal to the damping coefficient divided by eta squared, right? So M, B, and K are the usual mass, spring, and damper components of the mass spring damper, okay? And eta was that transformer ratio, and we defined it on the previous slide. Okay, so let's talk a little bit about these guys. So first what I'm going to do, I'll just write down what the impedance of this LCR is. See LCR, and I'm writing it in terms of the Laplace variable S. It's just the sum of each of these impedances. So it's Lx times S plus 1 over Cx times S plus Rx. Okay? And remember that the resonant frequency for this guy, omega n, is equal to, I'll write it like this, omega n squared is equal to 1 over Lx Cx. Okay? And so if I substitute S equals omega n into the LCR impedance equation, it will turn out that Z LCR at S equals omega n is equal to Rx. Okay, so the impedances of the inductor and the capacitor cancel each other at resonance. You remember when I talked about about the ideal oscillator, it's really the way the oscillation works is that it's energy being transferred back and forth between energy stored in the capacitor to energy stored in the inductor, or in terms of like a mass spring damper, right? It's kinetic energy in the mass gets transferred into potential energy in the spring. And that will just happen forever if there's no damping, right? So basically the energy just transfers back and forth between those two elements, and there's no impedance in the circuit at the resonant frequency. And so really the only thing that prevents the oscillation from happening forever is this Rx. And you'll notice also that we could think about this as if you look at this impedance, right? You remember I plotted the frequency response of the LCR tank. If we go back to this guy, right, we looked at this thing here. So this amplitude here and this phase. So at resonance, it has 0 degrees of phase, right? It looks like a resistor, and that's exactly what this thing is saying here. So if you notice here is basically the phase angle. So the phase angle of Z LCR at omega n is equal to 0 degrees, right? Because it just is a real number. It's not a complex number, and so there's no phase angle. And at low frequencies, just like it shows on this slide, right? At low frequencies we have plus 90 degrees of phase, and above the resonance we have minus 90 degrees of phase. And so one way that you can think about this thing is like at low frequencies, hopefully we know at low frequencies, like for DC, right, the impedance of the capacitor dominates, right? It looks like a very high impedance. The inductor basically looks like no impedance. And so at low frequencies, this guy looks like a capacitor, okay? And then at high frequencies, the opposite is true. So this guy kind of looks like a short, and then the inductor dominates. And so we could say that basically at resonance, it looks like the resistor. At low frequencies, it looks like a capacitor, and at high frequencies, it looks like an inductor, okay? And this is also, if you remember way back when I talked about mechanical equivalence, right? We said that at low frequencies, the thing obeys Hooke's law, right? And so the spring dominates. And indeed, right, that's the same thing here, right? So this is the C element represents the spring. So at low frequencies, this is dominated by Hooke's law. And then at high frequencies, it's the mass that dominates. And indeed, the mass is the inductance, right? Okay, so if one important thing is that at resonance, the thing looks like the series resistance Rx, and so if you wanted to know at resonance the amplitude of the current that you're going to get, I sub x is going to be equal to Vn divided by Rx, right? This is just Ohm's law, okay? And so, right, this Ix is the sense signal that we're getting out, and we want this to be big. So big sense current requires small Rx, right? We want the motional resistance to be small, okay? And if this was, if we were talking about a resonator that's used like in a radio system, typically radio systems use 50 ohm characteristic impedance, and so we'd like Rx to be like 50 ohms. So for RF MEMS, Rx equals 50 ohms is ideal, right? And so if you remember, right, if when I talked about this damping, right, we like the damping B, mechanical damping, to be as small as possible so that we can get close to this Rx to be 50 ohms, right? And it turns out that it's very, very hard to do that. And the other tool that we have, right, if you look at the equation for Rx, let me just sort of highlight this guy here, okay? So B is the mechanical damping. So we first of all, we want to make B small. So we want B small. Small damping. So B should be small. And this usually means vacuum. Vacuum package. The MEMS structure. So there's no air to create damping. The other thing we can do is basically make eta big. Large electromechanical coupling. Okay? And if you remember, let me make a new slide for this. So the equation for eta, right? So eta is equal to dCdx times the bias voltage, right? So basically, big eta requires Vp should be big, and dCdx we want to maximize, right? Okay, and I'll also mention, right, that because if we look back at the equation, right, eta appears squared in the equation for Rx, right? So it's really, you know, because it's eta, Rx is equal to B over eta squared. So that says basically 10x increase in the bias voltage, Vp, gives 100x reduction, lower series resistance, right? Lower motional resistance. And so oftentimes people, when they are, you know, reporting about electrostatic MEMS devices, they operate these things at 100 volts because that's the only thing that they can do to get low series resistance, okay? And so every factor of 10 increase in the voltage gives you a factor of 100 increase in the, or reduction in the series resistance. Okay, but what else can we do? Well, dCdx, we can make that bigger. And so dCdx, let me write this down. Let's do it for a parallel plate capacitor. It turns out most people use parallel plate capacitors nowadays, not these comb finger structures, because the dCdx is just not big enough. Parallel plate capacitors, so they have much bigger dCdx than a comb drive. So the picture that I drove, much bigger dCdx than a comb drive. And so that picture that I drew on the previous page, like almost nobody makes comb drive oscillators anymore. They're sort of a interesting research topic, but certainly for RF MEMS, nobody uses comb drives. They are used in gyroscopes because you need large displacements in those things. So you don't care so much about the motional resistance. You really want to get large displacements. So if we go back to the parallel plate capacitor, right, we had dCdx. Hopefully this is probably getting old for you, right? It's d by dg, let's say, of this epsilon naught A over G, right? That's the parallel plate capacitor. I'm doing it Actually, I can do it the right way. I'll do it. I'll be a little bit more careful here. dc dx, sorry, not dc dx, I want d dx of epsilon naught a over g minus x. And so what we get is, when we evaluate this at the nominal operating point x equals 0. Okay, so we're going to take d dx and we're going to substitute x equals 0 into this guy. We get epsilon naught a over g squared. Okay, so eta is inversely proportional to g squared. So I'll just sort of write that in green. Basically, eta for this parallel plate capacitor, right, is epsilon naught a over g squared times v polarization voltage here, right? And we could write then that Rx is equal to B times what's got eta squared in the denominator, and so we get G to the fourth over epsilon naught A times Vp. Sorry, we want this to be on the bottom. Vp squared. Okay. So, oh boy, the gap appears to the fourth power. Okay. So Rx scales with g to the fourth power. So let's say 2x smaller gap gives us 2 to the fourth. 2 to the fourth, that's 16x lower motional resistance, right? 2 to the fourth here. I'll look at that more carefully. Ooh, so that means that we should use small gaps. So I'll write it here. Basically, we have high voltage. Okay, and down here, basically small gap. That means if you happen to have like 2 micron lithography in your clean room, and your competitor, let's say at Georgia Tech, has 0.2 micron lithography in their fancier clean room, right? They could produce 10 times smaller gaps, right? They get, well, they get 10 to the fourth, right? So if you could go from a 2 micron gap to a scaling two micron gap to 0.2 micron gap will give you 10 to the fourth, right? 10,000 times lower Rx. Wow! So you should use small gaps. Okay. So that is most of the math that I wanted to emphasize here. I think I talked about everything that's important on this. So let's look, for example, what now, instead of having this sort of gigantic comb drive resonator, what people make nowadays are mostly things that are basically parallel plate transducers, certainly for high frequencies. And so this is a picture of a modern electrostatic MEMS resonator, and this is what's called a Lamé mode or a wine glass resonator. So it's this sort of square structure, and it has, let me try shading these guys, right? So it has some, these are the electrodes here on these sides, and here, and here. These are the electrodes. And the thing that I'm going to kind of shade in purple, this is the actual resonator. And although it looks like in this picture, it looks like the, so I'm going to shade it in, be very fancy. So this is the, this is basically the resonator body. These guys are the electrodes. Okay? And they look like they're touching, right? But if you look in really, really close here, there are these tiny cuts between the electrode here on the left. So I'll write it, this is the electrode. And this is the resonator body. This is basically the moving mass, right? and this is the air gap. And so how is this made? It turns out that this is a group from Cornell. They made this device using a technique called a focused ion beam, or a FIB. So they used a FIB to cut these slots. They went in with a focused ion beam and they just went zook right across, one cut for each electrode to separate this. And it's written down here. Here's the characteristic natural frequency of this thing here. L here is the side length of this square, right? So that's L. And you see here's the 10 micron scale bar beneath where I wrote L. So this thing is like 30 microns across. The air gaps on this thing are like, I want to say they're 50 or 100 nanometers. So very small. So 0.1 micron, 0.05 microns. And the other parameters in this equation here for natural frequency is G is the shear modulus, and rho is the mass density. Okay, so for this equation you could calculate the natural frequency for this guy. So G and rho obviously are dependent on the material, and L is the length, so you can pick the length of this guy. And the resonator body is a square, and it's held at the four corners. So you see there are these four anchors that go to the sides, right? They go like these are the anchors, right? So anchor, 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 like that. Okay, and so this is what it looks like when it's oscillating, right? You can imagine that it sort of flexes upwards this way, right? So it's moving out in these directions. Let me use a different color so you can see it more clearly, right? It's moving outward this way, and it's moving inwards this way. And obviously there's a conservation of volume here, right? So it doesn't increase in its volume, and so it's sort of expanding in one direction, contracting in the other. And those are the tethers. They're at the nodes here, right? So the maximum displacement is at the antinodes. So let me mark these guys. These are called the antinodes. And the nodes are where there is zero displacement. So we put the flexures where there is zero displacement so that the thing can resonate, and it resonates kind of like a free body. And then here's the electrical diagram. So so there is a DC voltage applied to the body of the structure, and there are these input drive signals, right? So we're applying some nice sinusoidal waveforms here, and then this is the sense is from the top and the bottom, right? So there's sensing current going this way, right? So this is the same kind of resonator structure as I showed on the first diagram, right? There's a polarization voltage for the resonator. There's an input signal here and an output signal, and so this comb drive is kind of a representative example. This Lamé mode wine glass resonator has the same kind of electrical connections, right? There's a DC voltage, and that again, that DC voltage is going to determine part of the electromechanical coupling constant eta. And there are these sense electrodes here and the drive electrodes. And so you could obviously it's easy for you to calculate eta because these really look like parallel plate electrodes, right? They have some length L and some height to them, to the thickness of the structure, and some air gap that's very small. So this is sort of a typical kind of structure that people use for modern resonators. But electrostatic resonators are not the whole story, because there are also piezoelectric MEMS resonators, and in fact the only filters that are in large-scale production right now are actually piezoelectric. So the dominating technology for piezoelectric filters, well, there are the surface acoustic wave filters, but there are also what are called bulk acoustic wave filters, BAW filters, and that's what's shown on this page here. So they're called bulk acoustic wave filters because they are acoustic waves, vibrational waves that occur in the bulk of a piezo material. And so this top picture is showing a picture of one of these devices. So we have a top electrode and a bottom electrode here, and in between them is this piezo layer, right? So the piezo layer is this, what I'm kind of shading in as purple here. Okay, so this is a piezoelectric layer, and we by applying a voltage across the piezo layer, right? So there's basically like V plus here, and let's say ground on this bottom electrode. So like this, right? So that's grounded, and that generates a field, and that generates strain. And so you could imagine that as we sort of resonate this thing back and forth, that we can set up a stress field that looks like this. It has basically its minimum stress points at the sort of top and bottom of the structure. Okay, so this you can see is basically this this structure is basically half a wavelength of a vibrating wave, right? So if we imagine a vibrating wave having a wavelength like this, what we're saying is basically we have the top electrodes here. So this, we would call this as lambda here being the wavelength of this oscillation, and so this thing here is half a wavelength, lambda by 2. Okay, that's what this characteristic thickness is here. So these bulk acoustic wave resonators work by having an acoustic resonance that is with the half wavelength of the resonance is equal to the thickness of the resonator. And, well, how do they trap this acoustic energy? Well, it turns out the way they do this is by having an air on top of the structure and beneath it. So this structure is made by making a membrane. So it says here support layer, and beneath it, it says here's the bottom cavity, right? So there is an etched cavity underneath the resonator structure. And the reason they do this is because there is a large impedance mismatch, mechanical impedance or acoustic impedance, between this solid structure and air. Okay, and so what that means is that it's very hard for energy, acoustic vibration energy, to transfer out of this resonator into the air. So that means that when we put energy into this structure, there's very little loss to the air, and in other words, this thing can be very high Q, because remember, Q is a measure of the energy dissipation. So by having air on the top and the bottom of this this bulk acoustic resonator, we can make a very high quality factor resonator. The thickness of the film is going to be equal to half the acoustic wavelength. And this kind of structure that's drawn like this is usually what's called an F-bar. So it's called a film, like a thin film bulk acoustic resonator. Okay, that's this F-bar structure. Okay, and I'm going to switch that off for a minute so I can show you the other one. So now down below here, also this is the same kind of structure. So there's a piezo layer in between, and there's like a top electrode and a bottom electrode. Right, so this is the top electrode structure, here's the bottom electrode, and again we're going to basically apply V plus to this guy, and then this one is ground. But now instead of etching away a cavity underneath this thing, the way that this is what's called a solidly mounted resonator. Solidly mounted. Sometimes it's called a solidly mounted bulk acoustic resonator. Solidly mounted. Right, so there's no membrane here. No air beneath the structure. Okay, so the way this works is they make what's called it's a sort of an acoustic mirror structure, and that is sometimes what's called it's called a Bragg reflector. So if you don't know what that is, you can look that up. Basically, the way that it works is we have low impedance materials that have a low acoustic impedance alternating with a material that has a high acoustic impedance. And so this low impedance layer is shown sort of at the top. It's this kind of crosshatch thing, and the high impedance layer is shown darker. And each of these guys has a thickness that's equal to 1/4 of the wavelength, lambda by 4. So quarter wave reflectors, and they're alternating high and low impedance pairs. Okay, so they also use this kind of Bragg reflector structure for lasers, but there it's not the acoustic impedance, but they're looking at the difference in the refractive index. And so what you can see, this sketch shows that you get another half wavelength going through these quarter layers, and you get a reflection at each interface. And the idea is that the energy is kind of reflected back into the resonator, and it really only takes a few of these pairs. This is showing 3 pairs of high and low impedance layers to make a good reflector. And so the idea is that this Bragg reflector looks like an acoustic mirror. And so the idea is that it reflects the acoustic energy back into the resonator structure. So in the one case, in the F bar, we rely on the big impedance mismatch between the resonator and air, and that's what keeps the vibration energy inside the resonator. And in the other case, in the solidly mounted bulk acoustic resonator, we have a Bragg reflector that reflects the energy back in. And this is made up of, typically they use tungsten as the high impedance layer, so this is tungsten, sorry, W, and the low impedance layer is usually oxide. Okay, so it's not particularly complicated to make this thing. And these are in mass production, and your phone almost certainly has an F-bar in it. Another way to make these sort of piezoelectric resonators is this is called a contour mode resonator. And this is from a paper from Gianluca Piazza's group. He's now at Carnegie Mellon University. And so what this looks like is the green layer here is the piezo material. Okay, it's a piezo material. It's usually aluminum nitride. Some people have made these with zinc oxide, for example. Same thing for the F bars, right? So they're either aluminum nitride or zinc oxide. And so, and there were these top electrode and bottom electrode. These are interdigitated electrodes, so they're sometimes called IDT transformers, interdigitated transducers. And if we look, okay, so here's the input voltage, here's the output voltage, and so let's imagine that we have like let's say this is like V plus over here, and the output is more or less going to be, it's going to look like a ground. We're going to put that into an amplifier that kind of makes this terminal look like a virtual ground, okay? And so if we were to now imagine the electric field lines that are directed from the plus terminal to the minus terminal, right? They look like this. So this is the E field, okay? And again, now from the red to the blue, right, we have opposite electric field lines, okay? So that's the E field. This is inside the piezo material, right? So we have, and I can show it. So here's a cross-section view down below, right? So if we have a plus electrode, then we have E going this way, and then we have E going this way here, right? And so what you could imagine is now we have electric field that that is directed like this, and now what's happening is that, well, we could imagine that because of the piezo coefficients, right, we're going to have, let's say, some positive, because the field is positive, right, we're going to have some positive displacement upwards, and it's going to go to 0 in the middle of this thing, and then it's going to go down, right, because now we have a negatively directed electric field. And so this is like, if we thought about the displacement waveform inside this material, it goes from essentially null in the middle of this guy to a null here, and there's a null in between. And so hopefully by considering this thing, right, you can see that again, this is lambda by 2 here. And so the spacing of these electrodes is going to be equal to lambda by 2, where lambda is the acoustic wavelength. Okay. So I think I'm going to describe that a little bit more on the next page. So these electrodes are spaced by half an acoustic wavelength. And this picture at the bottom that shows the nice rainbow pattern, this is the strain field, actually I guess is the displacement field inside this resonator. So you have basically 0 displacement within each electrode. One reason you want to do that is you don't really want to stretch the electrodes, because there's loss associated with stretching these metal electrodes. So they are at 0 displacement points. There's maximal displacement in between the electrodes, like where I wrote E here. So these are like, in terms of the nodes and the antinodes, right? We think about, this is like a node here. This is a node here. And the antinodes are maximum displacement would be in these regions, right? So antinodes. Max displacement. right? And so the idea is that in any of these filters, what we're trying to do is we're making them, they're going to oscillate at a particular characteristic acoustic wavelength, right, corresponding to a desired frequency, and that's how we make a filter out of this thing. So if there's a cross-section view that shows like a structure, one of these guys, and so the acoustic wave is shown in red here, right? So that's this thing is the acoustic wave. And here's the electrodes, right? So they're input electrodes. Maybe I'll use the highlighter for this, right? So here's an input electrode, here's an input electrode, here's an input electrode. And the output electrodes are every other electrode, so I'm kind of shading it in here. And the idea, again, just like it's sort of shown here, right? The electrodes are at 0 displacement points, right? They're like this, and you can see that, you know, between the in and the output electrode, you got, in this case, you have like a positive displacement and a negative displacement, and a positive and a negative, right? Because, again, you can sort of imagine how the field is directed. So the electrode pitch is set at lambda by 2, like it said down here, lambda by 2, and that's equal to C is the acoustic velocity in the material, and F is the operating frequency. So for a given operating frequency, if I know the acoustic velocity of my material, I can define where I want to put the electrodes. Typically that's about, you know, for a 2 gigahertz resonator in aluminum nitride, you have something like a 1 micron. The acoustic wavelength is like 4 microns in aluminum nitride at 2 gigahertz. So each electrode is about a micron wide. And high acoustic velocity is desirable for high-frequency filters because you'd really like the electrodes not to be too small. It's hard to make electrodes once they get to be smaller than about a micron. And so you'd really like to have a high acoustic velocity so that the electrodes can be a little bit bigger. Okay, it makes it a little bit easier to make them. All right, so let me talk about micromechanical filters. So how are these sort of, now we talked about individual resonators, and it turns out that usually what happens in these resonator structures is they're actually made of coupled resonators. So before I really talk about, oops, so here I've been using, all right. Let me insert a slide before I do this one. So let's imagine that we just have, here's a mass and a spring, and then another spring and a mass. Okay, so these are 3 different resonators on the same chip, let's say, okay? And each of these guys has a characteristic frequency, omega naught is equal to square root k over m, okay? These are 3 resonators. And they have 3 resonances. And they're all at the same frequency. All at omega naught. These are called degenerate resonators. Degenerate resonators because they have, their frequencies are identical, okay? So it's basically degenerate modes are these what are called these equal frequency modes. Okay. So now what we're going to do on the next slide is we're going to say, well, what happens if we couple these guys? So now let's say I am able to introduce a coupling spring that now connects this resonator to the next one. Okay, so there's like a K1 to 2, right? This is like mass 1, this is mass 2, this is mass 3, let's say. Okay, and we assumed initially that each of these guys has the same mass. So I'll call this K1, K2, K3. And so when I wrote omega naught is square root k over m, so K1 equals K2 equals K. K1 equals K2 equals K3 equals K, and M1, all the masses and the springs are equal. Okay, so now we have a coupling spring between mass 1 and mass 2, and let's have a coupling spring between mass 2 and mass 3. So now what happens? Okay, so we have these three resonators. They're called degenerate initially because they're not coupled to each other. They all have the same resonant frequency. And now we're going to introduce some coupling springs. Well, it turns out that, like as it says here, coupling removes the degeneracy of resonant frequencies of free-running oscillators. Okay, so if we couple these resonators together, then what will happen is that these three, now what happens is we still have three resonant frequencies, but they happen now not to overlap. They're split now. And so hopefully I can convince you, just if you think about this a little bit intuitively. What's not shown in this picture is there's actually the springs that connect these guys to ground are missing in this picture. So this is sort of an oversimplified picture. But right, so there's a spring on this guy, and there's another spring going to ground for this guy here, and another spring going to ground for this guy here. Okay, and so on and so forth. But hopefully I could convince you. So now in this first mode here, all these masses are moving together, okay? So the effective, and these springs are undeflected. K12 and K23 are undeflected. So they don't do anything, unstretched. So they contribute no stiffness. And so basically this frequency is just omega 1 is going to be square root of, well, we have 3 times the mass over 3 times the stiffness, right? Because here's this K, this is K, and this is K. 3m over 3K. So it's just the original frequency, omega 1 square root K over, oh, sorry. It's 3K over 3m. Square root K, omega 1 is equal to, turns out this is the omega naught, right? It's the same as just the individual oscillators on their own. Okay, without the coupling. And that turns out to be the lowest frequency. There is a sort of intermediate frequency now where this guy is not moving. Okay, he's not moving, and so his spring actually doesn't matter. And this guy has his spring right to ground, and the other guy has the same thing. And so M1 and M3 are basically oscillating symmetrically, and neither one of them knows about the other. It's exactly like M2 is fixed to ground. And so now what we have is that K12 is adding to K1, and so we get a different frequency now, right? So here's omega 2 is going to be square root of K1 plus K12 over just the mass here, right? K1 being K and K12 being, okay, so there's that one not moving. And then there is the highest frequency one, basically when all the springs are recruited into action. And now, so all three of these guys are moving together. And one way that we could think about this is now like M2 and M3 are kind of at their closest point. So this is like minimal displacement here, and this is maximal displacement between these guys. And so this ends up being, so now everything is moving here. All three move. All three move. And so now all three spring constants matter. And I'm not going to calculate this frequency for you, but it basically has the highest stiffness, right? It has all three masses moving, but it has all the coupling springs are in action. And so this ends up being the highest frequency. Okay? So the idea is that if we had, let's say we're able to make, at the very beginning I talked about, we made a chip where we have three identical resonators, and they were just happily oscillating on their own. They all have the same nominal frequency. Now I'm going to introduce some coupling springs between them, and now I can make a combined oscillator that has these three resonant peaks. Okay, and it turns out, right, that we could actually do this coupling between resonators either using mechanical springs, right, the compliance of those springs, or we could couple them together using capacitors, right, because those are electrically, if we talked about the equivalent circuit models, the compliances look like capacitors, and so we can either capacitively couple the resonators together, or we can connect them with actual springs. So this is how people make filters. Okay, and so for example, what's called a ladder filter looks like this. It looks like a ladder because it has some rungs on it. And so now we have over here, so here's the input signal, here's the output signal, and each of these little pictures where it's showing this little picture like this. This is the symbol that people usually use for quartz oscillators, and that is equal to 1 mechanical LCR. So it's an RX, an LX, and a CX. So this is one oscillator. One mass spring damper system. Okay? And so now what these are is we have basically one MEMS oscillator, second MEMS oscillator, and a third MEMS oscillator, all in series. Okay? So now they're all connected in series. And then at the same time, what we have is we have some what are called shunt resonators that basically connect from the input terminal of the series resonators to ground. Okay? And I'll explain this a little bit more later, but the idea essentially is that by having, so if we go back to this picture here, by having coupled resonators, now what we can do is we basically have more control over the frequency response. So hopefully I can convince you that, and this is kind of shown on maybe one of the, actually I'm going to jump to one of the later slides. So when you only have one resonator, there's only one kind of frequency response you can get. All resonators have the same second order frequency response characteristic. And so by putting resonators in series, then we can generate more interesting filter profiles. So I'm going to jump ahead to the slides a little bit. I'm going to go here. So high order resonators. So by putting more resonators, like in this ladder filter, by having coupled resonators, we can make frequency responses that make basically different kinds of filters. And so what this plot is showing basically for a single resonator, right, we have this kind of characteristic thing with one little peak like this, right, and it just looks like this. If we had two resonators that we had coupled together, well, now we're going to have like the first resonator bump and the second resonator bump like this, okay? And then if we had three resonators connected together, we can make something where it's got like 1, 2, 3 bumps like this, okay? And so if you guys have ever thought about filtering things, well, this second order guy, he has, like we talked about this before, on either side of the peak, he has a slope. Actually, I'd better do it in the same color. On either side of the peak, this single resonator system has a slope of 20 dBs per decade, so not very steep. Okay, by having two resonators, then I get 40 dB per decade. And by having three resonators, I get 60 dB per decade. And these are on either side of the resonance, right? And this may be a little bit surprising for mechanical engineers. You're used to thinking about 40 dB per decade for a second order system. But remember, we're talking about velocity, so it's 20 dB on either side. 20 dB on either side. And so adding more resonators in series gets us more steeper slope here. And this is starting to look like, remember we talked about filters in the last lecture, this is starting to look more like a brick wall. Okay, so instead of having this kind of first order roll off on either side of the peak, now we can have a very steep roll off. We have more poles, steeper filter, better, as it says here, higher order is sharper roll off, better stop band reduction. And we can have like a nice square passband. So basically it's kind of flat. There's some ripple in the passband, but it's more or less flat. So we can pass the signals that we're interested in. This is like a 455 kilohertz resonator. And so we can have a nice flat passband, and we can have sharp skirts on the sides. Okay, so that's the idea in these things. Okay, so those are the kind of responses you would get if you just had resonators coupled in series. Now, if you look back at the ladder filter, a ladder filter has also these shunt resonators, and what these guys are doing is, the way to think about this is that if we just talked about series resonators, they would look, right, the three resonators in series would look like this. Series resonators only. Now what we can do with shunt resonators is we can make them have, and remember the idea is that at resonance, each of these series resonators has its minimum impedance, right? It just looks like Rx. It's the motional resistance at resonance. And so these guys are essentially the input signal at resonance for each of these resonators is passing through, right? So it's low resistance through at resonance. So these are like low resistance at resonance. Low resistance at omega naught. And then the shunt resonators, well, if they were low resistance at omega naught, that would be bad, right? Because they short the input to ground, okay? So we want these to be high Z at omega naught. But we can be smart. If we make them low impedance in the stop band, right, where we don't want the signals to go through, they'll short everything out. So by adding the shunt resonators, you can do this. So this is like a ladder filter. Okay, so we added some shunt resonators that have low resistance just before, they have low resistance in the stop band. Okay? And so that's why these filters look like this, so that they get these very sharp skirts with that really null the frequency response near the resonance. And this picture on the left is actually showing one of these ladder filters. This is actually a bulk acoustic wave ladder filter, and for a cell phone. And you can see on the bottom, this is a Infineon part. So Infineon actually doesn't make these anymore. They sold this division to Avago. But this is a typical filter that would be inside your cell phone, for example. And each of these things, right, we can look on the, here I'll use the same color. Right, so we have 3 series resonators, 1, 2, 3 series resonators. Each one of these guys is a bulk acoustic wave filter. So they look like capacitors, but they're piezoelectric capacitors, right? So if we remember, go back to the picture of the what the bulk acoustic wave filter looks like. It's like this one that's shown on the bottom here. Okay, so it just looks like a piezo material with the top electrode, and there's some acoustic reflectors beneath it. So these, what you see in the picture here, are really the top electrodes of these, the series resonators, and then these are the shunt resonators down here. 1, 2, 3, 4. Okay, so just like it's shown in this circuit diagram. Series resonators, shunt resonators, and this is what's used for filtering signals in your cell phone. You can see the wire bonds over here, right? These are the bond pads, right? Over here on the die. This thing is a couple of millimeters across, and so each of these filters is on the order of like 200 microns square. And you'll notice that they have sort of funny non-square shapes to them. And part of the reason for this is that they intentionally shape them such that they don't have, if they have parallel sidewalls, it's possible that you can have also acoustic modes that that can resonate in plane. And those are undesired. So there can be other modes, other vibration modes. And if those vibration modes are near where you're trying to operate the filter, they create spikes. They basically, you can see the resonant peaks. And so they create what are called spurs. So they make these things kind of oddly asymmetrical to avoid those spurs. Okay, so I'm going to take just a little break right now.